Hello, my name is Jean Cherlinsky-Ortega, and I'm here to talk to you about how some models with millions of parameters avoid overfitting. Here's an overview of the talk. First, I'll describe an impossible phenomenon. This is that deep neural nets with too many parameters generalize well. That is, not only do they have low training error, but they have low test error. Recently, it's been discovered that this impossible phenomenon also exists in linear regression. A linear regression with too many parameters also generalizes well, sometimes. But the fact that it does it ever is also surprising. And since then, there have been some papers that have tried to help understand this phenomenon, and it's focused on the role of misspecified features. This paper I'll talk about. And the important thing is because it's linear regression, we can have more mathematical understanding because linear regression is a much simpler model than a deep neural net. Let me back up one moment and describe better what is impossible in case to some people the success of deep neural nets seems natural at this point. So in statistical learning theory, we know that too many parameters perform poorly. The motto would be simple is good. Despite knowing this, people discovered that deep learning performs well using millions, sometimes even billions and trillions of parameters. That is the impossible phenomenon. But let me rewind once more and review for people that step one, simple is good. Why do we believe this? Simple models with few parameters are better. Well, one reason is what's been called Occam's razor. Plurality should not be posited without necessity. It just seems like if you can explain something with two causes instead of three, and you have to choose which explanation, the explanation with two causes should be chosen because it's simpler. All else being equal, of course. The other reason simple is good is that it's more understandable to humans. When we're trying to explain or discuss a phenomenon or understand a medical diagnosis, it helps to have two causes that explain it rather than, say, a million. But there's another reason we've preferred simplicity that is mathematically rigorous and also empirically observed. It's that simplicity has been more accurate if you look out of sample. In sample, the more complex model can do better. Out of sample, the simpler model does better. Because of this, when we do techniques to choose between different regression models, for example, we don't just choose the one with the highest explained variance, or R squared. Instead, we have these other criteria we use that we minimize. One of them is the Ikaika information criterion. And roughly speaking, it's how much information you get per parameter. So if you add too many parameters, you start getting less information per parameter. And another one that's sometimes been used is the BIC, Bayesian information criterion. These type of criteria are there to help us avoid picking an overly complex model. For example, if you're familiar with the R language, here's how you would perform a stepwise regression in R. There's an intercept-only model at the very least number of parameters with just the intercept. Then there's a model with all the predictors, which is the intercept plus all 10 predictors in this case in the MT-CARS data set. And then there's a call you can make, this step call, that starts with the intercept model and starts adding variables forward until at the end you hit the model with all the parameters. As you can see here, it stopped on step 4. The intercept model plus the WT variable plus the CYL variable plus the HP variable. So it stopped here because 4 parameters was enough rather than 1 plus 10. So it chose a simpler model. And here you can see the AIC was the criterion. Initially, as we added parameters, the AIC was decreasing. The minimum was achieved here at an AIC of 62. If we'd added, it tried adding a 5th parameter and the AIC went up, so the procedure stopped. So this shows an example of the tooling we have to help us prefer simplicity. If you focus on just the error, the out-of-sample error, this is an example, a schematic idea of what's going on. So the number of parameters are on the x-axis. The error is on the y-axis. What we find is as we add parameters, this red line initially decreases. In the case of the previous example, the lowest error, out of sample error, is at 4 parameters. That's the optimum. As we add parameters, this out of sample starts going up. And the AIC is a mathematical way to do it rather than using cross-validation. But it's the same idea. You can also calculate excuse me, this out of sample error with a holdout data set, the test data set. Now, the U-shaped curve that we saw for test error is in contrast to the training error. The training error, which means fitting within sample, always goes down as the number of parameters increases. That's that dashed gray line. Below that optimum number of parameters, we are underfitting, and above that optimum number of parameters, we are overfitting. Let me also show visually what the difference is between underfitting and overfitting. In overfitting, there are these points, and we have more parameters than number of points. The same number of parameters as points, and you can see that this jagged line can connect all of them. So there's perfect in-sample fit, 0 error in-sample. In this middle diagram, there's only the intercept parameter, 1 parameter, and so the best fit line is going to miss a lot of the points. There's fairly high in-sample and out-of-sample error. Well, I'll discuss out-of-sample in a moment. Finally, if you look on the right, there's the just right number of parameters. It's a line that doesn't necessarily touch every point. It doesn't have 0 training error, but as we'll see in a moment, it generalizes well. Here I've added an out-of-sample point, just one to make it simpler, and shown how each of the models might do with respect to it. The overfitting one happens to miss it by quite a bit because this jagged happened to jag at the wrong spot. The underfitting one wasn't too far off, but it was still off. The just right got pretty close. So it is when we're talking about the out-of-sample error that the just right number of parameters really matters. There is also a mathematical explanation for this U-shaped curve. It's breaking down the error into bias and variance. The idea is as the number of parameters increase, the bias decreases, but the sampling variance increases. So the optimum is the sum of those two, and that's why it's somewhere in the middle. For very few parameters, for underfitting, you have high bias, causing the total error to be high. And for too many parameters, even though bias is low, the variance is high. So this is a bit of a schematic way of representing bias and variance. The green lines are the bias, and it shows that the underfit model has high bias. This yellow line of the model is never going to get close to the true model, which is the black. And the black is if you knew the noise-free version of the data. So even in the noise-free world, the yellow line would have these green error bars because it can't bend to the correct shape. So bias is having the incorrect shape. Sampling variance is a bit harder to understand. These are the examples with overfitting, and it shows that every time we get a new sample of the red points, so on the left is the original sample I showed, on the right is a sample of new points, this yellow model completely has to change its jig and its jag. Every data set makes a completely different fit, and this is what we mean by high sampling variance, that this adds a form of error. It's overfitting is the word. Now, if you look at the just right model, it has a good balance between bias and sampling variance. If you look at the gap between the yellow fitted model and the black true model, it's very small in both samples of the data, the original sample on the left and the new sample on the right. It's a bit more biased on the one on the right, but on average, it will be low, and we look at the average bias. Next, if you consider the sampling variance, you can see that the orange-yellow fitted model line doesn't change that much between the original sample on the left and the new sample on the right. So it balances error due to bias, which is the gap from the true model, from that shape issue, and sampling variance, which is the wiggliness you get from slightly different sampling points. So if you hear the phrase that simple models with few parameters are better, now you understand why. Think of this picture. I myself was heavily invested in this idea because in graduate school, I participated in a research team that looked at how simple heuristics make us smart. We were arguing that many times, although people wanted to do complex models, they didn't need such complex models. And even our idea of rationality, perhaps, should be revised in light of this. So for me, it was a big shock when I started hearing about this impossible phenomenon within neural nets. Let's go back historically and see how this phenomenon developed. In the 2000s, there was a contest called ImageNet to classify images. It had a set of images such as these two on the left, these birds. One of them, the correct label was hen. I might have called it chicken, but hen was what they said was correct. And for the other image, robin was the correct label. And the algorithms had to come up with these labels. At 2010 or so, the best error rates were around 25%. So that means they actually got 75% correct, which is pretty good. Nevertheless, the models used in ImageNet had relatively few parameters, maybe 10s or 20s. But there was always a group of people who felt that you could do stuff with more parameters because, after all, the brain has a lot of neurons. And they kept trying and trying and trying to build a deep neural net for ImageNet. In 2012, a team succeeded. They built not only just any neural net, but a deep convolutional neural net, which they called AlexNet. And it blew the competitors out of the water. Whereas the previous best error rate was 25%, this achieved an error rate of just 16%. And as we mentioned, this defied the expectations of past experience and theory. AlexNet had 60 million parameters, and there were only 14 million images. So it had many more parameters than examples to train on. Nevertheless, it had much better out-of-sample error, 16% versus the runner-up of 25%. Early on, it was thought that perhaps the change was that maybe it's something special about images. But this kind of result, where the number of parameters is many more than the number of examples, has been found again and again and again in many domains. For example, in 2016, the game of Go was beaten by AlphaGo, which was a combination of many different models, but it includes deep neural nets too. And even though the number of parameters is hard to give, it's a lot. In the paper, they mentioned that they had to train more than 50 GPUs for 3 weeks. So this is a lot of parameters, and yet it was able to play this complicated strategic game that previously people thought would be a lot harder to win, because it's much harder than chess. Then in 2020, the domain of language was taken over by deep neural nets, in particular by transformer models and such. GPT-3, for example, has 175 billion parameters, and it excelled in a variety of language tasks. But just to give one example, lambda sentence completion. This means there's a sentence there, the boy went to the park. One word is removed, such as went, and then the algorithm must come up with that word. It has to generate the word that fills that in, which is a difficult task. The runner-up before then got 68% accuracy. GPT-3 bumped way ahead and got 86% accuracy in 2020. So this idea that millions and even billions of parameters can do well on data sets, what should have been overfitting, is a scary, amazing, impossible phenomenon when I saw this coming out of my graduate school background. And I was fascinated. I couldn't deny it anymore after seeing all these examples, 2012, 2016, 2020, image classification, languages. This is a real thing. And as TJ Sejnowski said in 2020, these empirical results should not be possible. This U-shaped curve says having that many parameters is bad. But in 2018 already, an article by Belkin and others looked at the U-shaped curve and found that sometimes you got what's called double descent. The U-shaped curve was not incorrect. It was just incomplete. The idea is that the U-shaped curve is on the left part here. If you go past the point where the number of parameters are equal to the number of examples, which is the interpolation threshold, you can sometimes reach another domain called the overparameterized domain, where the test error can go down again. If it does go down again, this is double descent, is the word they gave for it. Now, when they wrote this paper, all they did was observe this phenomenon in a variety of data sets for a variety of models. They didn't yet have an explanation, but at least seeing this said what we said before was not completely wrong. It was just incomplete. And that's the left side here. So just to explain more about what this interpolation threshold means, it's the point at which this training error, the dashed line here, goes to 0. It's the point where there's enough parameters to perfectly fit the data. That's what we mean by interpolating training data. What's odd is that there's now many possible fits, so you'd think it wouldn't generalize well, so what's happening? So P equals N means interpolation. P is number of parameters, N is number of examples. Overparameterized, just to give a visual way of thinking of it, is when the number of parameters is far more than the number of points. So if you look at this schematic here, instead of just connecting the points, the yellow line, the fitted line, has a bunch of extra wiggles that are there. There are way too many parameters. There should be very high sampling variance. Now this is something we have played around before and we've had solutions before, but the thought is maybe there's something about these network models and the geometry of their high dimensional parameter spaces that allow them to navigate efficiently to solutions and achieve good generalization, contrary to the failures predicted by conventional intuition. This was in the T.J. Sejnowski's paper I quoted before. So the thought is there must be something special about neural nets that avoids these extra squiggles happening that would make it have a terrible high sampling variance and terrible test error. And then this impossible phenomenon was discovered in linear regression. Just as a reminder of how simple linear regression is, it's basically just a bunch of linear equations. Here it is in matrix form. We have n observations from yi to yn, and then we have a matrix typically called the design matrix. This represents the data set. There are n rows for the n examples, and for each one we've measured the parameter values, the p columns from x11 to x1p, and then for all n rows. So the data set is the y's and the x's. We then try to fit the data with just p parameters, which is the same as the number of parameters we had the columns here. We're trying to determine the best b's to fit the data and to minimize these residuals in some way. So here's an example where I've made some code in R to show exactly what the paper is going to show that I'll show you in a minute. On this data set where there are n equals 10 observations, the interpolation threshold was reached at p equals n. At that point, the training error goes to 0. That's the light blue line that's below. The test error indeed went up very high at that point where p equals n. But what's interesting is if you go beyond this point, if you add even more parameters, the test error started to descend, then it descended more, and eventually the test error got lower. Let me walk through that later. But the question is, how do you fit that? If you think about that matrix equation I showed you, if there's far more columns than rows here, you can't invert the matrix, which is normally what's done to solve the linear regression, to estimate the betas. So you need to find a different way to estimate those betas. We could use gradient descent, just like neural nets use. Maybe there's something special about gradient descent or stochastic gradient descent, or these methods that helps us find a good solution. Another thing that's often done in practice is regularization. There's ridge regression and lasso regression, but in short, there are ways to limit the parameter space, so we aren't exploring all of it. In lasso regression, we're trying to find a handful of parameters that are most used. In ridge regression, we're averaging them. But I'll talk about a third method because it's the most amenable to mathematical analysis. And that's instead of using the inverse, we're going to use the pseudo-inverse. This is what Dar et al. Did in their paper, where they examined double descent in linear regression. So as a review for the inverse of a matrix, if we have a matrix X, we're seeking the A, such as A left multiplying X equals I, the identity matrix, the zeros with a diagonal of 1. So, I times anything is going to be itself. That's why it's the identity. If we rewrite that equation as AX minus I equals 0, it then helps us see what the pseudo-inverse does. In the case of the pseudo-inverse, there is no A that can solve that equation. So instead, we minimize AX minus I. We find the A that minimizes that with the L2 norm. The point here is we can quickly calculate the pseudo-inverse without gradient descent and study it analytically now. That's why this is a powerful viewpoint instead of looking at double descent in deep neural nets. So here again is the picture I showed you with p equals n. And the point here, though, is that double descent won't occur on just any data set. So you won't always see this red line go down. This is where the understanding of the paper comes to help us figure out when this phenomenon does and doesn't occur. I specifically constructed this data set in the way the paper recommended to get this phenomenon to happen. So here's the paper, Dar et al. 2021. They studied overparameterization in linear regression analytically, and they found a rich variety of generalization behaviors when the number of parameters p was greater than the number of examples. Their paper is called A Farewell to the Bias Variance Trade-off, ? An overview of the theory of overparameterized machine learning. It discusses the theory in general, but it focuses a lot on the linear regression case. So here are some of the conditions for double descent. They have it all in mathematics. I am summarizing some of their words myself here, and I did check with the authors if they thought this was a good enough summary, which, there's always some loss of information when you turn into words, but here we go. So of the 4 conditions, the first 2 are low dimensional signal structure in the data, where signal means denoised, and low effective dimension in the data, a few large eigenvectors. Most of you are probably familiar with eigenvectors, so that's an easy one. I'll also talk about the signal structure and compare them. So the signal structure is also known as the intrinsic dimension, and these pictures help explain it. So in picture A, both the signal structure and the effective dimension are 2. We have a plane in a 3-dimensional space, but all the points are confined to the plane and they are symmetric in a circular shape. In B, we've squeezed those points. They're still in the plane, but we've squeezed them in so that they have some dominant eigenvectors in some directions, this angle, and then a shorter eigenvector in the other direction. So its effective dimension from the eigenvectors is between 1 and 2 now. But the intrinsic dimension is still 2 because they still live on a plane. It's not until we squeeze them all the way down to a line that the intrinsic dimension drops to 1. Of course, there's also now 1 eigenvector, and they agree exactly on the number of dimensions. But B still shows they're basically aligned. Even though they have slightly different dimensions, the directions they're going in are basically the same. And that's an important condition for number 3, alignment. The highest signal data dimensions must be aligned with the highest effective dimensions, the largest eigenvectors in the data. So 1 and 2 should still be aligned. Now these conditions are not the focus of the paper. I'm going to focus on their 4th condition, which is there's an abundance of low signal but non-zero signal features in the model. Let me talk a bit intuitively about what that means. Suppose we want to predict university exam scores. There's 2 data sets. The scores data set, which consists of past exam scores from areas that are relevant to the entrance exam. So for example, a math exam, a language exam, a logic exam, and a social media data set, which has data sets that were convenient, that are collected in our life. So for example, the students' Twitter posts and likes, the location of their posts, where they posted from, Instagram, and so on. Now, it might seem at first totally irrelevant, but there's some signal in there. So for example, if their Twitter post comes from a library, there might be a higher chance of having a higher exam score. Or if their like is about a history topic, maybe they're going to have a higher exam score. The data set that's the scores data set has well-specified features. These are all highly relevant. In contrast, the social media data set has an abundance of low signal features. They are misspecified. They don't fit kind of the core dimensions of what's driving exam scores. So in short, the paper would predict that double descent would occur in the social media data set, but is less likely to occur in the scores data set. Unfortunately, I don't have access to these data sets, the university exam scores or the Twitter posts or whatever. So to demonstrate what this paper is saying, I needed to find a different data set. So here's what I found. There is an empty cars data set available in R. It stands for Motor Trend Cars of the Year. it had, I think it was 20 different models, and for each it had 10 different parameters. These are the parameters, number of cylinders, displacement, and so on. So this is what I would call a well-specified data set. So I wanted to make a misspecified version of this, something with an abundance of low signals. So what I did was I added random noise. Now there's different ways you could do it. Go ahead and run your own experiment. But we just need the average noise to be in there. A lot of average noise, low signal. It doesn't need to be per parameter. So what I did was I kept the original 10 parameters, and I added parameter 11, 12, 13, 30, so 20 more with random normal noise, 0 mean, standard deviation of 1. So that is my misspecified data set generated from a well-specified one. Then to run a simulation, for example, for 3 parameters, I chose 3 parameters from the empty cars data set, fit a line, and then measured out a sample error. For the other data set, empty cars with random, I chose also 3 parameters, but here I had a high chance of getting the random ones. 2 out of 3 on average are going to be the random ones. It's going to still try to fit a model with 3 parameters and then predict out a sample. So it's pretty tough on the empty cars with random until you get more parameters. And here's a comparison of the test error on the 2 data sets. The red one, the misspecified one, empty cars with random, shows exactly what the paper said. It peaks since I limited the data set to just 10 cars in order to conduct this test because it wasn't naturally wider than long. I limited it to 10 cars, so the interpolation peaked at 10 parameters. And then in the misspecified data set, as I added parameters, test error went down. In contrast, in the original well-specified empty cars data set, I have the classic U-shaped curve. And you can see a bit of a U-shaped curve on the red line too. They both have a little bit of it, but the blue one is there's no opportunity for double descent because I used all the data anyway. And the paper says even if there were other parameters, it's unlikely to help. So in short, if you have well-specified features like the empty cars data set, the lowest error happens with few features. This, I believe, is 3 parameters. If you have misspecified features, the lowest error is with lots of features. Here it was minimum at p equals 30, which was all the parameters. In part, that might be because then you're guaranteed to always get signal and not just noise. However, in this case, the lowest error didn't happen in the noisy data set with 30 parameters. The lowest error was in the original data set. So if you with correctly specified features and no noise. Now, that won't always be true. The paper has some conditions where this won't always be this way, but in this data set, that's how it was. One way I think of this is that the domain of statistics tends to have these well-specified data sets, like the empty cars one. There's a reason that empty cars was a classic in regression textbooks. It is the right kind of data set for our tools and for using the AIC and picking small models. Machine learning has more of the kinds of data sets where it helps to add a lot of parameters, such as very noisy and coming from social media. That's the domain of machine learning tools. Okay, Jean, that was lots of theory. Just tell me what to do. I got a little lost in all this talk. So here it is. Think about which type of data set you have. If you have well-specified features, select a model with few parameters. Simplicity still rules. If you have a data set with a lot of low signal features, collect as many features as you can. You need lots of parameters, and you're striving for double descent. You're striving to get down that curve below the error that you had before, the second descent. So the wisdom that simple models with few parameters are better is mostly correct, but it's only when you have well-specified features. So that's how I'd update that wisdom. I would also add a new wisdom. More features are better when you have poorly specified features for a good core signal. That was what the Dar et al. Paper said. Now there's a lot of other kinds of data sets than just those types. And those have a variety of generalization behaviors, which can be characterized by future research. So in summary, consider which type of data set you have, the well-specified features or low signal features. The one warning I have about this is that all these comparisons are within a model class in the paper. They were all in the paper, linear regression and linear regression. It's not really addressing linear regression versus neural nets, but there probably is some truth to that comparison too. We just haven't developed the theory. I'm going to speculate and say a lot of the times a linear regression with few data points versus deep neural net with many data points will follow many of the same patterns that this just tell me what to do says. In other words, well-specified features use a small linear regression, low signal features use a deep neural net. That was the core message. Let me add 2 reflections on this. First of all, successful overparameterization is related to stuff we've seen before. I call it impossible, but we did see hints of it before. Ensembling of many models always did better with more models. More was always better, not just a few. Boosting and bagging are techniques that also benefited from adding more and more and more. These were hints that adding more models reduces variance and leads to better generalization. It does not have the high sampling variance problem. So it's not as new as I made it out to be at first, now that we can reflect and look back on it. The other point is, why did we only notice this now? We have known about linear regression for centuries, so why did we only discover double descent now? I would argue because of our data sets. It's only now that we have an abundance of low signal data sets. Now we're constantly collecting data incidentally. It's not well specified. It just happens to be an output of your Twitter posts and your Facebook and other things like that. Our digitized world has produced this abundance of data. It's the type of data that's better for double descent. Whereas before, someone manually collected the data on those motor trend cars of the year. If you find this fascinating, here are some references to follow up on. The core bibliography, the Belkin et al. Paper that defined double descent is at the top. The Yehuda Dar paper that described the mathematics and came up with the 4 parameters is the second paper. And the third one has those wonderful quotes I had, but it's more of an essay than math. It also doesn't talk about the solution very much. Other than that hand waving, it's something weird about deep neural nets. So that's the core bibliography to read more. I also have a blog post which describes pretty much the content of this talk. And the code, this GitHub code, if you don't like how I ran the experiment with the empty cars data set, please run your own. And for now, that code is in R. I hope to have a Python implementation soon. Thank you very much. I hope you have found this topic as fascinating as I have.